All right. Hello, everyone. Welcome to our third lecture of ECS165. So today we're going to take sort of a detour and really sort of step back and think about why the storage and indexing are an interesting problem. Okay, so let's get started. And so the basic question is why is it important to have an indexing structure? What is it important to have in a storage structure? What is it going to allow us to do? And we're doing this also in the context of modern databases. Is we're going to look at some of the advanced way data structure that allow us to do both efficient storage, indexing, and the storage layout as well. So basic question. So this is the most fundamental basic question that we have in relational system or in general any database system. And the question is, how do I find what I'm looking for efficiently? At the end of the day, that's the most important question, is that sure, what I'm storing, I want to make sure that it's securely stored, that it will be remembered, it will never be wiped away, I can always recover it. Sure, those are all important information, important elements to have. But the other important piece is that, well, I'm looking for something, I'm looking for an answer, I have all this data, how do I find the desired information very quickly? And we're going to, and so how quickly we can find an answer, it depends how complex the question is. How complex the question is depends the expressiveness power of the query language. And so that all kind of highly connected to one another. And so when we talk about SQL, there's an expressive power of certain question can be posed, and we will have complexity, so we can do a complexity analysis of how long it takes to answer such question. But for the purpose of at least today, we're going to look at a very simple kind of questions. And this simple API is actually not only is the API that is often supported by key value store. For example, earlier today I was asked about Firebase. So Firebase does support this basic API. But more importantly, the milestone that we're going to be doing in the course for this quarter, it's actually going to be focused only on these APIs that we're going to talk about, the simple search queries. So what do we have here? Set of data points. Just, we can start with integers. And for the most part of our milestone, even for this course, we can just focus just on integer only. So now the question is, I want to search, and I want to search for 76. So how do I go about finding 76? What are some of the strategy? Given this is what we have, given this is the data that I have, sort of, I have a bunch of dices, think about it, and I just throw them on the floor, and I'm looking for 76. And what would be the best way to kind of go about finding 76? What are some of the ideas? Of course, I can just stare at the numbers and kind of look at all the numbers one by one, but I'm literally looking at them one by one. So, but what even if I'm following that that perspective, somehow I need to start looking at this number. So what would be the strategy? What is the strategy that one can follow in order to find the number 76 quickly? And you can just share anything that comes to mind. There is no right or wrong answer here.
Sort the numbers first.
Nicole, go ahead.
Oh, we were saying the same thing, sort them.
Okay, so sort them. So we have two people say we want to sort them. So that means I have to look at every single number first. Then I have to look at every single number potentially multiple times, and then sort them, and then finally find 76. So in the long term, it may be the case that if I were to repeatedly do this search, the sorting would make sense. But maybe there's simpler ways. So I had one person, their hands up. Go on, please.
So what if I just start from a random like dice and then start like scanning either clockwise or counterclockwise until I reach 76?
Sure, that seems like an interesting idea. For example, just some figure, I mean, it's not exactly, but let's say that 66 is your random starting point. And then I could just start, look at its neighbor, and then maybe look at its neighbor. And eventually I come about and find 76. And what would be the sort of the best case scenario potentially is that maybe the randomly when I find it, actually the first number that I start with is 76. Or maybe when I take the counterclockwise or the clockwise direction that you mentioned, I find it after 1 or 2 iterations. But the worst case is that I end up looking at everything till I find 76. So it works, and maybe I get lucky and I find it sooner, and maybe I get unlucky and I don't find it. And maybe on average, I still have to look at half of the data because it could be anywhere. So maybe on average, if I could do an average complexity, maybe it could be half of the data. But that's definitely one possibility. Or I could maybe look at from a different direction. Maybe 91 was my starting point. As you said, maybe if you did another sampling, and then you could actually do start from one direction, and then you give up and you say, okay, you do a couple of in that neighborhood, and then you just start somewhere else. That could be a possibility. And then finally, maybe from the bottom, I can find 76. But again, if we kind of really to go and analyze this, most likely in the worst case, I have to look at everything, and then maybe I'm lucky, I find it early on, and maybe on average case, probably if you do analysis on it, we have to look at half of the data before you find what you're looking for, just on an average. The other thing is maybe you can think of as that you look at a batch of element at once. So again, just taking the exact random sample. So I took a random sample and I just look at its neighborhood. I took another random sample, look at its neighborhood. I take another sample, take a random element and look at its neighborhood. So again, that could be potentially another strategy. Any other thoughts?
You could put everything in categories ahead of time so you know what category to look in.
Exactly. So for example, if I have additional information like categorical data, if I know something about my domain, then I can do some pre-categorization or some pre-structuring of the data. Precisely. What is common? So there are two things you mentioned. One, you mentioned in the beginning, once you mentioned here. What is the common denominator between those two? Sorting and categorization. What's the common denominator?
There's some kind of rule that tells you where to look.
There's kind of some kind of a rules. In other words, there is an order. We're kind of imposing in an order. And if we do have an order, then we can utilize that order to find what we're looking for much more efficiently. Maybe that order or that structure is the notion of category, or that order or that structure is having a sorted list. So both of those are, seems to be going kind of converging on that idea of how do we find something quickly. Any other thoughts? Again, these are the questions that you're going to be looking at for your milestones. You have to make these choices as well. So this is, so for even for your first milestone, when you get together, these are the very questions that you will be kind of as a group discussing with one another. So what if I searching for a value that doesn't exist? Could I use any of the existing approaches that we talked about? Are they still applicable?
Wouldn't you just have the worst case anyway and then terminate since you iterated through all the stuffs? If you have
Exactly, but then you hit the right keyword there, is that well, you terminate once you looked at everything, but is there any way that I can have that early termination? How can I avoid, if the number 44 doesn't exist, is there any way that I can respond quicker before exhausting every element? So that becomes an important element or an important question to ask. Is that a possibility?
I mean, if the data is sorted, I guess already, if you go past, do some search mechanism on it, you could terminate it once you pass that number or the number is greater than the number you're looking for.
Yeah, exactly. So that's, so again, using that search order, we can essentially do that early termination. And again, we're really going to come down to this basic, simple question. Could we impose order to improve the search? Could we impose an order to be able to find what we're looking for that does exist as quick as possible? Or as it was mentioned, is that we could also utilize that order once we reach 77 and we haven't seen 76, well, we know that 76 no longer exists. So again, that imposing that order, that structure, again, it allows us to do the type of early termination as well. And that's a really basic problem that we're looking at, whether it's in databases, whether it's in the storage, whether it's in the indexes. So that's the key simple question that we are looking. So now, how do we impose order? And this is something that many of you have already kind of alluded to, is that what if I take my random set of elements and then just create a sorted order, and I can do in a ascending order, 12, 13, 21, and all the way to 99. And again, as all of you or many of you have mentioned already, then if I'm looking for 76, I can start from one direction and I can work my way toward finding that till I hit 76. And that 76, that would be the point of my early termination. So I don't need to look at 81 to 99. So I find it efficiently, or at least I have to look at everything only once. So it does provide some benefit. But what would be the sort of the average complexity of, even if you have this sort order, what's going to happen here? Well, on average, how many elements am I expecting to look at, even with this sort order that was mentioned?
O of n.
O of n, because you essentially have to potentially look at everything, and maybe the average complexity of it is that, well, sure, it's still O of n, but maybe on average, you need to look at half of the elements. But how do we kind of take it to the next level? How do we, now that we have a sorted order, how do we get this even better?
Can't you just use a binary search?
So what does that mean? So tell me conceptually, what does it mean? Now, so we have an order. So conceptually, what does something like a binary search would allow us to do?
I think you just start at half, right? And then if the value you're looking for is greater, then you do that for the upper half, and then you recurse on that.
Okay, that's good. And there was another comment. What was the second one?
Oh, you just pretty much store it in such a way where when you're navigating, you use a key.
So the basic idea is that, so if you were to kind of sort of conceptualize what that really we're doing, is that can we have a systematic way of pruning our search space? So normally we had to look at everything till we find it. And now that we have this structure, can we go on and improve the search space by pruning? Of course, the early termination thing can also be answered as we had mentioned. So if things are sorted, if you're looking for 44, we don't necessarily need to exhaust the list. Once we find that, well, element 44 no longer is possible to exist, then we can stop. So the sorting does help with both termination and regular search. But now we have an order, and how do we now impose a further structure to improve the search? And then the suggestion is, well, why don't we use some form of a binary tree? And basically the binary tree, what allows us to do is, for example, I divide my set in two, and 56 would be the common element in between. Half of the elements, smaller, greater than 56, could be on one side, the rest on the other. Now I'm looking for 76. It allows me to do pruning. So I can, in one shot, get rid of half of the elements in my set. I don't have to look at them. And I can only focus on the other half. And you can think of, again, repeating the same thing, or you could also now start thinking about, what if I introduce even a deeper hierarchy? The more hierarchy I introduce, the more potential of pruning that I have. I could prune half of the data, then I could prune another quarter of the data, and then finally I'm only left with the scanning just a quarter of the data. So I can substantially reduce the search space by, once I have an order, and if I now impose a structure, a further structure on my order, that allows me to reduce the search space. Any suggestion, any question, any comments at this point? Any challenges now? So is there any trade-off? Are we now with this model so far of adding the structure?
Would it be more, it would take longer to like delete or add elements?
That's a good question. So for that to really, we have to kind of actually talk about how to, because it's really abstract at this point, is that how is it the lower level are stored? If the lower layer was kind of stored in a contiguous block, and now I have to insert something, I basically have to shift everything to one side, then it would have been, the original model would have been harder. And if you assume, for example, in this form, those curly bracket on the bottom, each of those are like one contiguous block, then if I need to insert something into those blocks, I don't need to shift everything. I just need to worry about shifting one block. And if I were to shift one block, then that may cause me to split, and then the changes needs to go propagate upward. So if I were to inject something, let's say 35, and let's say each of these blocks can only hold maximum 5, then this need to split, and then the node 22 could potentially needs to be updated, and potentially that change could go all the way to the roots. So there is a propagation upward on the as a result of addition or removal. But still, my removal could only be bounded by the length, by the height of the tree. So I could now go into the complexity of the tree and say, okay, I have a login insertion, I have a login deletion, and I have a login search as sort of a property of maintaining this tree. But those are important questions. There's code complexity. And if you're now talking about building highly concurrent data structure, is that many users are constantly accessing this. What happens in practice, although this is a very simple structure, in order to do all these adjustments of the leaf or adjustments of all the inner nodes and the adjustment of the tree itself, to prevent concurrency race condition, a lot of locks needs to be held. So this index structure tend to become more contentious, and also the programming of it becomes more and more difficult because there's a lot more locking, and there's a lot more corner cases to need to be considered. So on the modern side of the databases, they say, okay, well, perhaps I don't need to have, I'm going to try to reduce the height of my tree just to reduce the necessity of holding many locks. Because you may, as you go down the tree, one way of doing it, you kind of maintain locks. So you make sure the path that you're going, no one else can modify it. They can read it, but they cannot modify it. So as you increase the length, well, there's more locking that may happen. So those are kind of other questions. And in general, the other question that arises with all these index structure, which we're going to look at it again every class we try to go a little bit more depth into these topics, is that at what point is it easier to just stick with a sorted list that we had initially? That basic idea is that I'm just going to have elements sorted and I'm just going to scan through my list, versus building a structure on top of it. And becomes interesting is that the structure that I built on top of it involves a lot of random accesses, versus the flat structure that we have, we can do a lot of sequential accesses. And sequential access is much faster than the random accesses. So now, so that becomes a trade-off. At what point would it make sense to pay the cost of the random access versus to just sequentially do a brute force search, because I can get much higher bandwidth in terms of the amount of data I can read per second with my sequential read. And that's applicable to both disk, memory, and pretty much any of the storage hierarchy. Any layer in the storage hierarchy tend to have much higher bandwidth when it comes to sequential as opposed to random accesses. So then those becomes interesting question to ask. The other interesting question to ask is that if I'm only looking for a single element, then maybe it is beneficial for me to pay the cost of a random access from 56 to 74 to 76, 3 random IOs, as opposed to do a full sequential scan of the entire data. Maybe that's cheaper to do. But if I want to read everything greater than 76, I want to actually read a larger set of elements, then maybe the sequential access will become more beneficial. So those are now becomes all the questions that when a query comes and then potential few plans are being considered. So the access control that we talked about last time, one access control could be just follow the tree, follow the binary tree, follow the B tree. The other access control suggestion is just simply do the scan. So when we come up with this different strategy of how are we going to do this search, and then we need to do a cost-based analysis of sort of estimating what the cost of each strategy is going to be. And then, well, we're going to choose the most effective plan that cost-wise. And maybe for some query, if I'm looking for 76 only, the best plan would be just do a scan index lookup. But if I'm looking for the range of elements, it might be the case that it's much better to just do scan the entire data. So again, that really comes down to generating the different kind of plans that we can apply in order to answer the query, and then estimate the effort, estimate the cost for it, and then choose the most effective one. Any question? So again, going back to the earlier things that we asked, early termination, again, the tree would allow us to the early termination. So if I am looking for 44, I still can just drop anything greater than 56 from the root and come to 22, drop the first half, and then I'm only left with this part to look at from 33 to 56. And I can do early termination after reading 55 because I know I already missed 44. So again, with this structure, would allow me to do that efficiently as well too with the early termination. So now, if I want to do a range query, so if I want to look from 76 to 91, well, then I can still use this structure. I can come to 56, drop half, come to 74, drop another quarter, and then kind of scan and find all the relevant value. And this is now become the point, is that at what point, as I mentioned, is that would it make sense to do index lookup versus doing a scan? If I'm starting to look at most of the data at the leaf level, might be the case that I don't even need to have any structure. I could just brute force scan the entire data. And if I'm actually looking at a large amount of data, I may not even care if it's sorted or not. I'll just scan everything, because sorting and the maintaining of the sort itself is a cost. So again, that itself brings another sort of a design point and another decision to be made. and looking at it, all the trade-off that it may create. So not only, I may not need an index, I may not even need a sorted file, I may just be sufficient with just scanning, just a basic scanning, and I can really focus on building a database that is super, super efficient on just scanning the data really fast, brute force scanning of the data. I can go the other way around and build a database that is highly specialized with navigating the data and pruning the data as fast as you can. That's also interesting. And one may be better for some kind of workload, and another one could be better for another kind of workloads. So again, the space of the databases, it's very interesting, and it's really dependent on the application. If you're Microsoft or if you're IBM, you want to be building a single database product, so you need to kind of have all the facility to at least cover the core general cases of 90% of the users, for example. But if you're that, or 99% of the user, but if you're among that 1% with a specific workload, for example, Facebook or Google, then they may not be able to utilize it. They may have to build specialized engine just for their own workload. So again, those becomes interesting. Yes, you have a question, please go ahead.
You said build a database that just scanned faster. How did you increase the brute force speed other than just finding a bare CPU?
So for example, one interesting thing you can do, you can think about is that, what if I'm doing multi-query optimization? So instead of answering every query at once, if I know that multiple of queries coming in right now, for example, can I scan the data once and be able to fulfill all the queries that are interested in the data? So that could be a very interesting optimization. And, or I could maybe even think about, so thinking of the traditional disk, which we're going to talk about this a bit more in the next session, is that the traditional disk is the way they have a mechanical device that's just turning. So we have a physically turning device. SSD doesn't have that, but they have a mechanical device is turning. And if I'm looking for a piece of data and the disk has already turned, I kind of have to wait for it to come back at the position that I'm interested in. So there's nothing I can do because the disk is turning at a certain speed, 7,200 RPM or 14,000 RPM. And that's been at that speed for the last, I don't know, 20, 30 years. It's very limited in terms of increase on the RPM, how many rotation the disk can do, a physical disk can do per minute. So if I miss my rotation, I'm looking for 76 and I miss my rotation, I have to wait for the next rotation to come. So now you can think of as a database completely structured in a way, as opposed to look at the query that comes in and then figure out at what point they can read the data depending on where the rotation of the disk is. So that's one model. The query comes and then you read the data that you want. So that's one model of the query processing. The other model is that forget about what the query is coming. The disk is running at this rotational speed. I just push the data upward and whatever query is needed, they grab it, and whatever is not needed, they just ignore it. And I continuously push data upstream, and whatever query is interested in, they grab it, and whatever it's not, they don't. And so that the benefit of it is that now I don't have to come for one query, wait a couple of rotation, go to another query, wait for a couple of rotation. I'm just going at the disk speed, and sort of filtering and pruning, whether you need it or not, so happening at the upstream. So that's a very different design, and that's could be a potentially interesting and novel design. And so that's one example.
Thanks.
Any other question? Again, in databases or general computer science or in general sciences, oftentimes nothing is written in stone. So there are current techniques and sort of they are efficient based on what we know, but we can always completely rethink them. Sure, if you're talking about the law of gravity, maybe that's we can't really change that. Maybe we don't have the right perception on it, but the fact that something is you drop a ball, it will drop. So that seems to be factual. But for many other things, especially when it comes to computer science and algorithms and thinking about a problem, oftentimes we can rethink it and we can come up with a different way. Sure, we have some theoretical result in terms of complexity, and we have proven that it cannot be done better. But oftentimes there's in between, there's just so much more open space to be just to be discovered and to be invented. And really, just kind of, I would say we're still scratching the surface across the board. And these are no exceptions. So now, can we do better? Can we spread the data more cleverly to improve the search space? And so we look at trees. The other things that are equally interesting and effective, and they have their own benefits and trade-off, is a hash table. And the idea is, instead of really structuring the data in a form of a sort order, that I can utilize that sort order and build a structure on top of that sort order to be able to organize my search. So that's all really done by using trees. So that's what the tree allows us to do, sort order. But what if instead I scramble the data and I can somehow remember how I scrambled my data and to be able to quickly find an element and scramble the data in a large space, because if I were to just, so put it this way, is that you just imagine that you have a bunch of balls and then you have a set of buckets. And you can say, well, if I throw all my balls in one bucket, then if I need to look for like the blue ball, I need to go to that bucket, a physical bucket that I put everything in there, like a storage bucket. Then I need to look at that bucket and remove all the balls until I find my red balls. But if I instead throw my balls in 5, 10 different buckets, and if I'm looking for a particular bucket, a particular ball, and I know in which bucket I threw it, then the more buckets that I have, potentially the fewer balls in each bucket. That means fewer things I need to look through to find what I'm looking for. So that's the basic idea. So with the hash table is that I want to spread my data across a set of buckets, and I wanted to do this as more uniformly as possible. So even if I have some distribution of the data that is highly concentrated, so for example, my balls are just different shade of reds, very close to red, just different slight variation of the shade of red. And if I just do a broad classification, reddish like balls go to this bucket, then the entire data goes to a single bucket. So the idea of this scrambling or shuffling, a randomized shuffling, is to try to do this in a random way as much as possible. So if there was any clustering of the data, unlike, for example, what was mentioned earlier, is that if I see a categorization of the data, maybe I categorize the data, then I can, based on that category, find what I'm looking for. But what if everything is in the same category? Then if I need to look for something, then I have to look at everything. So this is kind of almost taking a reverse direction, is that try to scramble it, try to randomize shuffle the data as much as possible, so that the amount of information that are spread across these buckets that I have allocated are equally balanced. So it's not that one bucket, there's so many elements in it and the rest are empty. So as equally balanced as possible. So I get a value, I hash it, and based on that hash value, I can decide on what bucket to put. So I got insert 81, and 81 maps to bucket 6 by hashing it, some random, applying some random mathematical function, and then modding it based on the number of buckets that I have, and I get 6. So 81 gets to 6. And anytime I hash 81, I'm always going to get 6. So if I hash 43, it may go to 10th bucket. If I hash 76, it may go to the 8th bucket. And then hopefully they're all random. And it may, if I hash 91, it may be the case that it also goes to the same bucket as before. So that's what we call collision. And ideally, we want to reduce the collision, because the more we spread the data, then if I'm looking for something, the fewer elements I need to look at. But whenever I have collision like that, then if I'm looking for 43, or if I'm looking for 91, I will always be sent to the 10th bucket. And at least in this form, I have to look at always, or not always, in the worst case, I have to look at both elements. So if I'm looking at 91, well, first I check, well, it's 43, it's no good. I go to the next element, it's 91 till I find it. Well, this list could just get longer and longer if the hash function is not effective. And then I could just hash, this is the same data that we had before. I just hash all my data, and this is what I come up with. And there's a bunch of buckets that have collision. So now if I want to search for 76, I have a constant lookup. In a single lookup, I could potentially find 76. So versus that, if I had a sorted list, I had to look at the entire list potentially till I find 76. I have to look at many elements. If I built a binary tree or any kind of tree on top of my sorted list, then I had to go through to the height of the tree till I find the leaf page that holds the data and holds 76. So potentially had a log n complexity in terms of the height of the tree. But when we're dealing with hash table, well, that's pretty easy, is that I just do a single lookup and I can get to my 76 elements. So, but now this becomes, so let me just pause here. So any questions so far? So we're looking through flavor. We'll look at trees, now we'll look at hashes. So what are the limitations? So what do you think would be a challenge or limitation for this structure?
Maybe having a very large data set, you would constantly hash or have collision or something like that. And then, not sure, it depends on how your hash formula is. You might have more imbalanced tables in general.
Mm-hmm. Yeah, that's definitely an issue. The other issue is that right now, if you notice, I kind of said we have a fixed size bucket. So set number of buckets. So what if I have more and more data? At some point, I want to kind of add buckets. Now, how do I add buckets? Does it mean that I have to go back and rehash everything? Or if I had initially started with a lot of data and then my data got removed, how do I now reduce my bucket size? So that could be itself whole another challenge, is the expansion and contraction, or the adding more bucket and removing bucket. That itself is an interesting problem, and it's oftentimes it's a difficult problem, especially in terms when you deal with concurrency. So yes, so that's an important one. What else?
You could end up with your data really clustered, especially if it's not very different from each other and it's not coming out separately in the hash function. Yeah,
so exactly. So now that's, if my hash function is not good, and I kind of preserve the clustering of the data, the categorization, and data just is highly clustered, then in a sense becomes ineffective. It just becomes a linear scan of a random order, because, for example, everything will go into the same bucket potentially, or the majority of the element goes to the same bucket, and all my searches goes to the same bucket. So again, I lose the benefit. What else?
The size of the hash table could get pretty enormous, I imagine, keeping up with a lot of data.
Sure. I mean, the size of that could get bigger and bigger, probably proportional to the size of the data that we have. Of course, in order to, if we get into the situation that in order to be able to have a balanced tree, a balanced hash table, meaning equal size buckets. In order to achieve that, if the number of buckets needs to be 100 times larger than our data, then it becomes very sparse and ineffective in terms of the storage. So it's going to add a lot of storage overhead. And so the bigger the data we get, we now have an amplification of 100 because that's the only way we can kind of avoid having many collisions. But if that number is very small, is that perhaps the size of the data is like 1.3 times, or the size of the hash table is only 50% larger or 20% larger, or 30% larger than my size of the data, then there is an amplification, there is an overhead, but that overhead is manageable. And that kind of goes back to the effectiveness of that hashing function that was mentioned earlier, but that definitely could become a problem. What else?
The larger your data set, the more likely that you have collisions, and then you have to find some way to resolve them or store them, and you could end up with a situation where you're doing a linear search.
Yes, so that kind of ties back to the question of how this hash table grows or shrinks. If I were to just come up with a fixed number of buckets and my hash table never grows, then yes, that issue happens. But then in order to alleviate that, there's a lot of work and a lot of research in the past 40 years is to talk about how do I grow my hash table? So as more elements are added, the structure gracefully increases in size to avoid those long collision lists. But then that growth itself is a difficult problem, especially when it comes to concurrency. A lot of these become a concurrency issue in terms of the challenge of doing it efficiently, of how much data needs to be locked. For example, if I need to, for example, rehash everything, potentially have to lock everything. And that could be very expensive to do. So that would be an issue. But some positive points. So what are some positive points of this structure?
It's a mostly constant lookup time.
Mostly constant lookup time, and I can just directly go to some buckets. I don't really need to lock leaf level. I don't need to lock the root. I may have to lock the bucket itself, but the amount of locking that is happening, it's pretty minimal. In fact, there are variation of this, of how to do this completely lock-free. So there are several work that allows, so we can do that with a lock-free mechanism or a latch-free mechanism. So with the tree possible, much more complicated, much more non-trivial than a hash table. So there's some performance, definitely there's simplicity in the structure. And if there's a simplicity in the structure, so then it's simplicity implementation and simplicity in concurrency. But how about some of the other kind of queries that we asked? What if I'm looking for an element that doesn't exist? Can this structure do that sufficiently or no? So if I'm looking for 44 and 44 doesn't exist, is this effective or no?
No.
Why not?
I feel like if you search for the key, I guess it would come invalid because it's not in there.
So it's effective. So I can, as long as I can do that.
Yeah. So if you search for, it's very effective.
Yeah. So I can quickly find that it's invalid or it doesn't exist, and then so that means effective. But how about the other thing? We looked at other type of queries. Is it effective for those as well? If you remember
it bad
what they
for
were?
a sequential search because it's random? So
definitely. So for sequential searches, that we basically have to just search out of order. We can start from the top, say 56, 12, 91, 71. So we can do that sequentially from that perspective, but it's going to be completely out of order. And if we're not really concerned about the order, then maybe it's okay. But if we are concerned about the order, well, the order is completely scrambled. So we basically have to read everything. And if you need to sort it, well, we have to sort it. So it doesn't help at all with that. What else? What other queries you tried earlier today? How about range queries? How do I do this? Can I answer this? Find everything between 76 to 91. And those numbers are highlighted in my bucket. So how would I do that?
Couldn't we just search individually for each number between 76 and 91 and see if it's there?
Okay, and is that an effective way of doing it?
It would be slow.
Why?
Yeah.
So what are the challenges with it? Why is it slow?
Because you have to search through. Oh, go ahead.
Oh, because you have to access the disk multiple times.
Okay, what else?
Pretty much you'll have, sorry.
Go on.
You would just have to search through the whole, like from 76 to 91, every number once. Instead, if you were on a tree system, you would have to search. If you find a number in between, you can just continue on without keep searching.
Exactly. So, and now if my range is from 76 to 91,000, then I have a problem. I basically have to enumerate. What other problem could it have? What simplification are we doing for this kind of for our data type? Is it just as effective for other data types? I mean, here we're looking at integers. What if it was a real number? How would it work?
I mean, your hash function, if it was good, it should work, right? And if you have something unique about your data to use.
So how do I do from 76 to 91 if it was real numbers?
It's not possible because the search space is infinite, I think.
Yeah, because that's the issue we get, because you have to, our hash function can only work with one. So I have to do 76.1, 76.2, or actually I have to do 76.11, 76.111. So you get just this infinite number that you have to consider. You can never get from 76 to 77, basically, if you don't know what the numbers were. So it may not even be possible. For certain domain, maybe it's possible. For example, for integer, maybe inefficient, but it's still possible. But for some domain, it may not even be possible, such as the infinite space that you mentioned. And of course, I mean, if you're just doing so to do the search, we'll basically have to start from 76 to 91, hash every value in that range, and then look it up. And then we're potentially hitting every single bucket till we find that answer. So it becomes not practical. And especially if we not consider real numbers, then that seems to be, we'll get into this infinite enumeration. So can we think of a way of doing this efficiently, even with hash table? Any idea of how to do it?
No.
Go on.
Oh, I was just gonna say, what if like we take the hash values and put it into like similarly to like a tree or something, so we have a range. Okay. So then, depending on the query, we can alternate between the two.
Exactly. So that's a good idea, but that's kind of saying we're not going to use the hash table. We're going to use a tree for ranges. It's valid, and oftentimes databases actually do precisely what you said. They have a hash table and they have a tree structure. For a lookup point, they may look at the index, the hash table index. For range queries, they may look at the tree. But how do we use the hash table to do the range queries? Is it even possible?
Could we just order the hash table?
Okay, that sounds interesting. What does it mean by order the hash table?
Well, I guess it would depend on the type of data, right? In this case, the buckets would go through the buckets would be assigned, I guess, based on their numerical value, or you could set each bucket to be a specific range. Like this bucket would hold whatever 1 through 10, the next bucket would hold 10 through or 11 through 20, whatever.
Yeah.
Sure. That would work. But what's the challenge with that?
I guess potentially sparse data, right? Like we just may never encounter those values. And then we have the dedicated space wasted.
Exactly. So for example, if you're dealing even with the domain of the integer, I don't know, we have a 32-byte domain, and so we have to really partition our space rigidly, let's say a size of 10. So there's 2 to the power of 28 or 29 partition that we're going to have. And as long as we're not going to have that many data points, as you said, there's going to be a lot of overhead. And the principal problem that the hashing solve is to avoid doing that pre-partitioning. That was that, so that you can say that the hashing, that's the exact challenge that you just described, is what is being solved by hashing. That very precise problem that you pointed out. Go on. Got a question?
Yeah, what if like we make how do we say, store it in a special way that every element remembers within a certain range where the other like stuff are. For example, 2 will remember which bucket 3 is in.
Yeah, that seems to be a very, very interesting way of doing it. All right, so let's, okay, sure. So I think you're hitting exactly what I wanted to say next. And any other ideas or elaboration of that idea? So what if we promote a set of value as seeds? Okay, this is like, this structure is called R hash. It's something that I worked at it when I was at IBM Research. So what if we promote a set of elements as seeds? And it could be just random set of element, like 34, 71, 91. Just 3 elements as seeds. And then, as it was suggested right now, what if I also remember, very simple, just every element, remember its next. So 71, remember 74, 74, remember 76, 76 remembers 81 or points to 81, 81 points to 84, 84 points to 91. Almost like creating a linked list among these different elements. So two basic ideas is that just every element point to its next larger value. Just need to look at the next value. Doesn't need to look at point to multiple elements, just one element. And then also have just a set of elements as seeds.
How does it know what the next larger value is?
So that becomes interesting. So now let's get the structure. Then we say, how do we insert? Because that's where we're going to find out what the large element is. So that's exactly the same question. I mean, that would be the next question. So let's walk through that. So now, what would happen if we want to search for something? Let's assume for now, to kind of, before coming to your question, somehow we know what the next elements are. Just for the sake of it, let's say we know what the next elements are. Somehow we got this pointer set. Now, if you want to search for what we did from 76 to 91, so then the way we can do that is that we kind of ask, find the largest seed smaller than 76. So we have a set of sorted seed. Ask them, what is the largest seed smaller than 76? And it's 71, okay? And then the next step says, okay, let's hash 71 and then I follow the next element, which is 74. Well, 74 is not what I was looking for because I'm looking for 76. From 74, I go to the next, I get to 76 that I wanted it, then get to the 81, then go to 84, then I come to 91, and that's my final element. So with having this pointers, just simply pointing to the next, and having a starting point, and this was the challenge that we had, the starting point, especially with that infinite set. We don't know where to start. What would be the right value? Is it 76.00001 or is it 76.021? We don't know, and you have to enumerate it. But with the sorted seed, or just a set of seed, doesn't have to be sorted. Sorted just makes it easier to search, but with a set of seeds, I can always find my starting point. The more seeds that I have, the more accurate my starting point is. The fewer seeds that I have, the less accurate my starting point is. The more seeds I have, I'm essentially also maintaining a sorted list on the side, so it becomes costly. And well, like if I have fewer seeds, the cost of managing a sorted seed is much less, but I may be off or maybe too off in my starting point of the search. So again, a nice trade-off happens. So any question before now going to the question of how do I even know these green arrows? How do I determine those green arrows? Is the basic of this? Go on.
Sorry, is there a name for this data structure? A formal name?
So the name that I gave it was rhash. So it's a pattern that I did back in 2014, 2015. So
wait, does every value have an arrow, but not every value is a seed?
No, every value has. So these are the. Do you see my cursor, by the way? There's the hand, or is that visible or no? Yeah. So these are the seeds. So I can promote a set of elements as seeds. So that's independent. So that's basically completely independent of this structure. Even these values don't even have to be an element of the hash table. This is just for starting point when we're doing range queries. Now every element is just pointing to their next largest element. I'm not showing all the arrows here because it would have been too messy. So I'm just showing a selected few green, but 12 is going to point to 13. 13 is going to point to, what's the bigger number than 13? I guess 34, or it's going to point to 33. 33 is going to point to 34. So all of those are there, are just not shown to make the diagram manageable.
So you only hash the seeds though?
No, you don't have to hash the seeds. The structure is identical as it used to be. So if I'm looking for 55, I am going to hash 55 and I can just find 55. If I'm looking for 81, I hash 81 and it's right there. But if I am searching for something, I'm searching for 76, and if I search and if I hash 76, so if you look at the previous example, if I look for 76, if 76 doesn't exist here, I don't know what to do. So then I have to do 76.001. 70.76.001 doesn't exist. So I don't know where is my starting point. So now with the seed, I can find the starting point, which is 71. And then from 71, then I can initiate my hash table. I can initiate my browse on the hash table. So from the seed, I kind of go into an element that is very close or potentially the first element in my search. And then from there on, I follow the pointer. I'm no longer going to navigate by hashing. I'm going to navigate by pointer chasing.
So it's a hash table with like a sorted linked list on top of it?
It's the hash table with a sorted linked list embedded in it. Yes, exactly. Along with just a set of random elements taken as seeds as a starting point, so that I know. So these elements, have to be actually in the hash table. So,
so the thing with the seed, are they the node of the linked list, or can it just be the value itself, and then you just continue to search for that?
So the seeds are just a value. So then you just hash it, find where they are, and then you kind of continue.
Okay.
Professor, and I assume that you update the seeds as you're inserting elements in the hash?
Yeah, so let's get to that. Yeah, so let's get to that, the insertion, because that's kind of go back to how do we construct this green arrow too. So now, how do I insert 79? So then the first step is that, well, I do hash 79. 79 goes to the 10th bucket. I insert 79. Okay, that's okay. But now the question is, I need to find, because now to construct the linkage, I essentially need to do a range query. I need to ask, what is the smaller value of 79? I don't know what smaller value than 79 is. I can try 78.999. I could try 77.99. I don't know what it is. So what I could do now, go back to the seed and ask, find the largest seed smaller than 79, and that's 71. So now I hash 71, I find the value 71, I go to 74, from 74 I go to 76, and 76 goes to 81. And I say, oh, that's the spot. So 76 shouldn't go to 81. So that's what happens. 76 should come to 79, and 79 now needs to go to 81. And that's how these pointers or these linked lists gets adjusted. Again, in coordination with the seed. It allows the starting point, and then you go and you modify the pointer. So that's the maintenance of the linked list, basically.
And you said that the sorted seeds are just random, or how do you know how many sorted seeds you want compared to the size of your data?
Yeah, so those are all interesting questions. So, so some of it needs to be done experimentally, and some of it you kind of want to maybe distribute it in a way that sort of creates some equal balance set. So maybe, can I find the midpoint, or can I find 10 seeds that the number of elements between these are equally balanced? And it's okay if it's not, but it would be some form of a statistical measure. So over time, you probably have to add more seeds as you add more elements, and you probably have to do some statistics on the data to help you. But those are all really interesting questions, is that how many seeds I should have, and how do I select the seeds? So those are some of them I would say even some of them are open question. Here is the focus is kind of, if you have the seeds, if you know the optimal set of seeds, what is the mechanism of how to do it? So now the next question is, what are the best set of seeds? And so that's a good question. And I kind of leave that as an open question. Any other question?
Yes, Professor.
Yes.
This might also be like another experimental question, but would it be advantageous to have, instead of having as a linked list, having it as a double linked list, so you can go like next or previous?
Yeah, I think that's definitely could be advantageous, and kind of allow. So one advantages of that is that if I'm looking for find the largest seed smaller than 79, I could also look for the smallest seed larger than 79. And if the smaller seed larger than 79 was closer to 79, and if I have a double linked list, so then maybe I can do my search in the reverse order. But if I see the largest seed smaller than 79 is closer, then I can do forward traversal of the linked list. So that gives you that availability. So that's an excellent optimization, and again, you kind of have to experimentally play with it. The one thing that makes double linked list hard is that this structure, as also what, as part of this is what we kind of showed, is that I can do this structure completely without holding any locks, completely lock-free data structure. And doing a lock-free data structure wouldn't be trivial. I wouldn't have to do it, for example, if you have a double linked list. So to make this structure, so there is no locks required in this data structure. I mean, that becomes a bit involved to go over all the details of that, but you can do it completely without holding any locks and still allowing multiple user accessing and changing the data simultaneously without holding any locks. And what allows it to do, it's kind of breaking it onto smaller pieces. You can do that easily for sorted lists. You can do that for linked lists. And well, the bucket, that's also, well, that's a simple structure, and the collision, or you can think of it that's as a linked list. So a linked list, we know how to do lock-free. Sorted list, we know how to do lock-free. And a double linked list is difficult to do lock-free. Although it sounds very simple, it's difficult to do. And if I give you an intuition, is that I can do lock-free one step at a time. And the way they do lock-free one step at a time is what is called compare and swap. I look at something and I know what its current value is. And if the current value that it has, it matches what I thought it was, it allows me to change it to a new value. So that's compare and swap is an operator that the processor provides atomic execution of it. Now, so for example, both of us wanted to insert a new element, and both of us want to make the 74 point to this new element that we're adding. Both of us will read the 74 pointer, and if the 70 pointer hasn't changed, one of us will go through and make the 74 point to the new element that we wanted to add. And one of us will fail, because as soon as mine goes through, the pointer gets updated, and your initial thought that what the 74 should point to no longer exists. So one of those operations fails and needs to retry. So by this basic, so translating all the operation that is happening in this data structure, using a simple primitive of compare and swap, you can construct the last restructure. But if I need to change double pointer, I need to do two things at once. I need to change the back front and a front for back and front, and the compare and swap, it only allows me to do one. And now doing two things, it becomes as simple as it sounds, it just becomes exponentially harder problem. There's no simple way of doing that. So again, the simplicity of the data structure, oftentimes we can make this very sophisticated, fancy data structure, but when it comes to the implementation, it's hard. When it comes to concurrency, it's even harder. And then that all affects in the usability and the practicality of it. So one key idea is to making it as simple as possible. And all the elements in this structure have that very simple. A linked list, a sorted list, and just a simple, like almost a trivial hash table. And the combination can be done lock-free. In fact, when we talk about LStore, the entire architecture of the storage architecture of LStore is going to be lock-free. You don't have to do it for your assignment in a lock-free manner, but the entire thing from concurrency to all the data structure layer, everything can be done in a lock-free way. And that was a design goal. So I'm kind of gonna come back to this problem a little bit more in the coming classes again as well. Any other question? So I guess I stop here because, well, I have to stop here since the time is, we're already over time. So now the next steps of, we talked about high level of indexing, and next is the storage layout. How does the data now laid on disk? So that's, we're going to talk about next week. And then we will go over the chapter 8 of our textbook, through another set of slides and kind of going a little bit more in detail, a little bit more formally into some of the topics that we talked about today and we'll talk about Tuesday. So this is a kind of, I want you to kind of get that high level view. It's sort of just thinking about the problem of indexing, thinking about the problem of storage, and sort of tap to your creativity. And we had a lot of creative conversation today. Many of you offer really interesting, thoughtful solutions. So really get to that mode of thinking. And that's the mode of thinking that I want for this course. So really think about these different problems. And for your milestone, most of it is open-ended. There is basic structure that is given, but how are you going to do your indexing? How are you going to design your disk? How are you going to even do the implementation? It's all completely open and it's up to you how to do it. And so I want that to happen even in our lecture, so that you really get into that mode of thinking, that just be creative and you can do things much better than what, of course you have to spend a lot of time and energy on it, but you can do things much more effective, much more efficient, much more simpler than what the status quo is today, with, of course, invested time and effort. All right, so if there are no further questions, then have a wonderful day, everybody.